Welcome back, everyone. And today we're going to start with a new topic: particle systems. I really want to start doing some special effects, something for fun, a lot of wow factor. Because I'm starting to get to a point where I want to start maybe think about making a mini game or something. So, and effects are really fun to do. They're really cool. They look great. They look fun. If you ever played with Unity, they have a very powerful particle system thing. It has like boatloads of features. It's easy to get lost and not confused by a lot of these features. So, but since we don't have Unity and we're building everything from scratch, so here we go. We're gonna do particle systems. And here's some images if you do a quick Google search of what a particle system entails. And a lot of them, when you search for particle system, you see it's kind of this a lot of particles or dots kind of grouping together to perform some type of effect. But in all honesty, it doesn't always have to be little particles. And a lot of effects like hair, like if you do, things like that, where you have like a bunch of particles or a bunch of lines really that are affected in a certain way. So yeah, there's a lot of images if you want to search for particle effects, and they look like just dots that you're moving around. And in essence, that's true. You're moving vertices, but it doesn't always have to be dots. I guess if you search for magic, like this effect, there's more than just dots. You have lines and you have circles that, I believe that these will kind of grow and glow. You have like something like this, something like a magical aura. You have a couple of dots that does it, but then you have these lines that shoot up in the air, and then you have the sphere that probably glows and spins, and all this is these are all particle effects. Like in the event of this, it's probably 3 particle effects on top of each other. You have one that kind of controls this, the little ball. If you watch the YouTube video, I actually didn't see the YouTube, so I'm not sure. But what I know of particle effects is that these lines are one effect, and then the dots are another effect. The dots are probably just your actual vertice particles. These lines will actually probably be quads with textures in them. So these are actually textured quads that you're actually affecting. So that's why I kind of said particle effects aren't always just moving dots around. You actually might be moving quads around, and those quads will then have textures in them. And of course, the floor is another quad with the texture in it. So yeah, there's like a lot of little things, and you can find tons of ideas online about particle effects. On YouTube, there's actually several people that teach you how to do effects in Unity. And that's what I'm kind of hoping to do, to go through these tutorials and how it's done using a UI tool like Unity, but then try to replicate that effect programmatically using JavaScript and code. So this way we have to write all the math ourselves and everything else. So we kind of have to learn to see something visually, and how can we interpret that into code. And that's probably another like a little side thing I want to do with WebGL too, is do that. Just find a bunch of effects online and see if we replicate it. So to do that, we need a particle system. To replicate a lot of these effects, we need to start building a particle system, some type of system that allows us to do these things. So that's what we're going to do today. We're going to start building our particle system. And normally when you do a particle system, you have to let me rewind back. Previously, before a certain feature existed in WebGL, if you wanted to do particle systems in WebGL, you would have to basically put all your vertices in a buffer and then render them. And in the next frame, you would then have to update all the vertices, because you have to go through all the calculations and like move, like let's say you want to move a dot up, straight up in the air. You have to calculate its new position and post it into the buffer, and then render it again, and rinse and repeat. And the more particles you have, the slower it became, because you had the CPU doing all the work, and then you had to push all the data into the GPU. with WebGL 2.0, we have something called TransformFeedback. TransformFeedback is essentially kind of like VAOs, but they give you a way to, well, they function like VAOs. Let me go back again. The way they're created and they're used, it's very similar to how VAOs are set up. So if you can do VAOs, then the way of setting up transform feedbacks is almost identical. What these features allows you to do is to actually have your shader code right into a buffer. So instead of having your CPU and your JavaScript calculate the next position of your vertex, you can actually have your shader calculate its next position of the vertex and then save it right back into the buffer. So next time you render it the second time around, you don't have to do anything on the CPU end or anything in the JavaScript. It just looks at the buffer, calculates the next position, saves it, and then renders it. And it just does it all in the GPU. This allows you to do thousands, if not millions, of particles on the screen with high frame rates, because everything is completely done on the GPU end, and GPUs are really good at doing things like that on its own. So this way, you don't need to deal with the CPU calculating things and then transferring everything back to the GPU. And like I say, if you have it like a million vertices you want to just render, that means you got to pass in like 1,000,000 times 3 plus more, because you have all these floats and things that you have to deal with, like vertex attributes that you might want to include, like colors and whatnot. So now that you kind of get an overview of what particle systems are and what we're going to be using to make our particle systems easier to render, make them very efficient, let's start looking at what our shader is going to be, because this is really a shader feature. Most of this is just shader stuff, with some WebGL code to kind of just get everything up and running. So we're going to add a new attribute that we can access in our shader code, and we're going to call it TransFeedback. And all you need to do is save an array of the name of the variables that are in your shader that are going to be basically your output, your output. And when I say your output is basically, let's say we go down here, we're going to do a bunch of calculations, and we're going to save those calculations into those feedback variables, right? And what those feedback variables does, it actually saves it back into the buffer. So like we have position, right? So we're going to read from a buffer, and we're going to get our position. We're going to do some calculations on it, and then we're going to update V position with what we changed A position with. So V position goes out, and it gets saved back into a buffer. Now, but the thing is, you're not updating the current buffer that you're currently reading. You have to actually set up two buffers. You have to set up two sets of buffers. You have buffer A and buffer B, and then for every frame you alternate. So one buffer is set up as read, and the other buffer is set up as write. So buffer A, let's just say buffer 1, because I don't want to confuse you guys with the A and V. So buffer 1 is set as read. So buffer 1 will then feed these attribute values. Buffer 2 is set up as write, and that's where these output values go. We go to the next loop, the next frame. Buffer 2 is going to be set as read. So buffer 2 will start feeding in the attributes, and buffer 1 would then be our output, would be our write. So like here, like the idea is, let me do a quick idea of how this whole feedback thing works. So let's say we just have, that's buffer 1, buffer 2. Let's do the same thing. Here's the thing. When you set these up, initially, they're both going to be identical. They're going to be completely identical. It's a shame you kind of have to do it that way, but They have to be identical. So when we create our two buffers, let's say these are our positions, and let's just pretend that this is one vertex. That's another vertex, and that's another vertex. I don't want to do 3 values per. I just want to make this a nice, simple example. So in our frame, we're reading from buffer 1. So we have this, we get this vertex information, and we're going to modify, saying, okay, we want to move this up to a position. So it's going to move up. And now when we go to this one, we say we want to move that one up as well, and then we move that one up as well. So at this point, we're done reading or rendering buffer 1. We're done. Next frame comes around, and we're going to swap them. Now, like I said, buffer 2 is now the read, and buffer 1 is the write. So the next time around, we're going to say, well, okay, we want to move this up as well. So now it's 2, 3, 4. And then the next frame happens, and we move this. So it's 3, 4, 5. And that's how transform feedback works. You have at least 2 buffers, and between every frame you alternate back and forth, and it allows you to basically create state. And by creating state, you can create motion. That means, because up until now, buffers have always been this static thing. And you can always set up as dynamic and then constantly update its values. But you can never, up until now, until we had transform feedback, we can have actually the buffers update themselves essentially using our vertex and fragment shaders. Actually, just our vertex shaders. Fragment shaders can't write. So everything has to be done in our vertex shader. And this is the magic. So since you say we're moving a particle, as you can see, we're linearly moving our particle up 1 unit at a time per frame. And that's what we're going to be doing. Don't need that. So these are going to be the 4 values that, or 4 buffers that we want to change. So for our simple particle, we want to know its current position, its current velocity, basically what direction and speed it's going, its age, and its life. Now, why you want to know age and life? Well, a particle has a lifetime. It starts somewhere and it ends somewhere. And the way we use transform feedback is basically to interpolate between 2 different states. Like I said, beginning of life and the end of life. So V position has your starting position, and for every frame, V velocity would change your position. That example I was doing, we're changing 0 to 1, 1 to 2. That's what velocity is doing. It's changing our position. And we're going to keep changing the position while its current age is less than the maximum age it is allowed to live. So if let's say it's at 0 seconds, it's been only alive for 0 seconds, its lifespan can only be 3 seconds. So by the time V age equals to or is greater than V life, we then reset the position back to a starting point and rinse and repeat. So this way, this particle gets recycled over and over again by using V age and V life. And for example, so here is our main shader. So the first thing we're going to do, and another important factor that we need to kind of bring into here, where is it? We need to consider time. Since we're dealing with age, we need to start passing in time. And there's some changes to fungi we had to do to make access to time a lot easier. So since we need to know the age, we need to start bringing in current time into our shader code. So first thing we can do is take our current time minus the age of our particle. Now we know how old it is. If the age is greater than its life, that means it's time to die, essentially. We do some math, and what here we're doing, I'm just calculating a random number. using GL vertex ID and uTime as parameters for our random number. So we get a random number, and we're going to do some random rotations, essentially. And you might be, what is 6.283? It's pi times 2. So I want to do a 360 rotation, and since we have to, everything has to be in radians, that's why we're doing this. So we want a random number between zero. I think between 0 and 1. That's what random will give us, a value between 0 and 1. So random number 0. So give me a value that's between 0 and 6.283 radians, basically between 0 and 360 degrees. I want a random position. So once I have the random angle, but that's what I want. What I'm doing, finding a random angle, I just do R, and then I use R as for length, I guess. No, yeah, I use it for length as well. Times cosine and sine. So basically, I'm getting the x and y position. Like I'm getting like a random xy position on a circle. So that's what we're doing here. We're getting a random position within a circle space. So it's also going to have a random length. If I wanted to be like perfectly around the circle, I would just say times 2, and it'd be the radius of a circle. But I want the position to be random within the maximum of 0 to 1 unit length. So now we have a bunch of random values. And like I said, this is the end of the life. So we're going to reset our position to 0. We're going to go back to position 0. Our velocity, we have our random x. We have our random z, which is the x and y position, if you want to think about it like on a flat plane, if you're looking at it. And then, so we know, like in the circle wise, where we're going to, do I have maybe an example of an idea? Yeah. Essentially, we're building this. So you have that circle, right? So we're going to start right here at the center point. And here's our circle. And we're trying to figure out a random spot anywhere within the circle that we want to go. So like that random part gives us the place. Then we just figure out a y position that we want to go. And the y position, basically how fast we're going to move, essentially, because this is our velocity vector. So we're trying to determine where in the circle we're trying to get to and at what height. So like how this goes here, so it's within the circle, but at that certain y position. So nothing gets beyond this circle funnel. Then we take our current time, save it as our age, and then we save back our life, which we probably don't need to update our life. Do we? No, we don't. We actually don't know. I don't think we need to. This is like one of these buffers that doesn't need to be updated, but I did it anyway for completion's sake. But we really don't need to change life, because life in itself is static. It's always, the life that you're gonna have is always gonna be the same. So let's say, okay, so that's how we reset a particle when its life is done. And let's say if the life, now during its life, we're going to take its velocity. You know what? Let's take this out for now. We'll add this back in later. So we're just going to make our velocity equal that velocity for the next loop. And then position, so we're going to take our position, and we're going to get only 1% of that velocity. But that's like kind of determines how fast we're going per frame, essentially. So we only want 1% of that total velocity added to position, and that position then gets saved into v velocity, which is basically our current position that we're currently in. which also gets saved into our write buffer. And we end up using that as the value to determine our GL position. And we save our current age to the next buffer because our age changes. Or actually it doesn't. So it changes based on this, really. Do we update that at all? No, we just keep using the same age. It's basically the starting point. It's a age is really the starting age, the time that this particle was kind of created. And that's really all to really updating the buffers, really. Like I said, it's these out variables, and you just kind of calculate them and you save the values, and the GPU knows to take those values and then save them into the buffers. All right, so let me go to the top of this, find new. So we're going to do some changes to our fungi to facilitate some things. So like I said, up here we got this new attribute, and we got to pass in these array of values, so we know what are the values that's going to be our feedback. So we need to pass those values in. So in GL.js, we're going to update create program text files, and we're just going to pass that in. So we can just pass it into our function that's called create programs. And here's our function, create programs, and it passes it in. And we're just going to have a quick check. Is it undefined? Is it not null? If it's defined and not null, all we have to do is tell GL to set up. Okay, so we know we have our program. We created our shader program. So we have our program ID, and we give it the array that we're passing in from here. So we're passing that array into here. It's a string array. And we're going to tell it that it's separate attributes. Now, there's also something called interleaved attributes. The big difference between these two is that what kind of buffer is the transfer feedback using. Separate attributes means every variable is its own buffer. Interleaved attributes means they're all attributes on the exact same buffer. Like we've done in the past, where we actually combine all the data in one single buffer, and you have to use what is it called? Damn it, I forget where's our create shader? No, it's not create shader. It's a create buffer. Oh man, I forgot what it's called. Strife. I think it's called Strife. Buffer size. Damn it, I forget what it's called. Stride. I'm sorry, Stride. If we're going to use interleaving, that means we have to create a buffer that uses the stride and offset values. Because let's say you have a position, age, life. They all exist in one buffer, and you have to partition the buffer into little pieces. So you have to define all the little pieces with stride and offset in our vertex attribute pointer. But essentially, it's a lot easier to use separate attributes. So this way, each buffer is separate. Like I said, like life doesn't really need to change. Once you set it up, it's something that never needs to be updated. It's just the overall life of the particle. Unless you want the life of that particle to be random, then every time you reset the particle, you set a new life. Which, like I said, it's something you can do. That's why I kind of did it as a completion. Because you can change a life every single time if you want to. And in this instance, I'm not changing the life of the particle. But if you want complete randomness, then yeah, each particle has a different lifespan. So that's something you can do. So that is really the only changes here, because and this is all you need to really set up our shader program to handle feedback, to handle the feedback variants. So this is our GL, and then we're going to our shader code. And let me scroll back up because we still have to do some more shader setups for it. So if I see, so like we have load shader because we're going to load a shader from the web server. So we're going to check. This basically does the actual check here. It's actually looking for this value, so it can pass into our GL functions. So it's looking for TransfromFeedback. If it exists, it grabs the value. Else, I want to make sure it's a null. I just want to make sure it's not like an empty string or anything else. So if it's undefined or whatever, I pass in that value. What else? I think that's it. I know, I'm sure there's more. So we're gonna load a shader. Has these two lines that are changed, so we can pass in our feedback values. Our shader builder, of course, we're going to pass in our values in here because we need to pass it to our create program shaders. Fine, next. And since we're doing certain things like time, we need to pass. This is new. Pass in floats as a uniform. So far, after 51 videos, we have yet to pass in an individual float as a uniform into our shaders. Now we kind of do. So it's just a new function, uniform 1f. Very simple, kind of like everything else except without the v because it's not a vector. And that is it for our shaders. Like I said, we only had to set up floats, and then just set up the ability to pass in the feedback through our shader builder stuff. And like I said, time is important. And time is created in our render loop, right? So our render loop is what creates our time. It determines our time. But we need an easy way to access it. So I decided to make delta time and since start a global variable that gets updated at every frame. So this way, anywhere in the code, I can load in fungi and check to see its delta time or since state. So it's easier to actually get these values anywhere in our framework now, instead of having render loop pass it into our onRender function, and then we kind of have to pass it on anywhere else. This way we can access it anywhere. So I'm just making it easier in this instance. So this is really more of a fungi fix, but we need this because we need time, because we need to know the age of our particle. So with that being global, so inside our render loop, we just save it. So once we calculate those values, we save it. We do it in run limit, and we do it in run full. So this way, for every loop, those values do exist. It's kind of like Unity. Unity does have a delta time that exists globally that you can access anywhere. So it's really the same idea. And that's all the changes we need in fungi to really start accomplishing transform feedback. Need that open. So now that we're on our test page, we're gonna load our shader, and we're going to use a new class that we're building called emitter, and we're gonna pass in our material because this shader also gets a material name. So that's it. So new emitter. And now here's our emitter class. This is going to be a bare bones example of how to get transform feedback working. Bare bones. So all this code, and when I say bare bones, I literally mean bare bones. I took away a lot of the abstraction, so we're going back to basics. See, I'm not using any fungi to do this. This part is we have to go back to basics, because I really just want to show you guys how it all lays out, and then maybe by the next video I'll abstract it all away, because then we don't have to deal with that anymore. So let's actually talk about what we're doing. So an emitter. An emitter is a name usually in a lot of frameworks and engines, is the thing that spits out these particles. So that's why I'm calling it an emitter. It's something that kind of just spits things out. It emits things. And we're drawing points. We're going to use points. So we're going to just do vertices. We're not going to do quads or any odd shapes, because ideally you can actually use any shape. You can use complex shapes like squares, spheres, whatever, and use each one of those as a particle. You don't have to use points or just quads. It could be literally anything. And certain effects actually require you to use some really funky shapes that are textured to really get some really neat effects. One effect I saw was kind of like a Dragon Ball Z aura. How someone does it, and I was really flabbergasted by it, because I never thought that that's how it's actually done. So this is one of the effects I want to do in the future, is a Dragon Ball Z power up effect, but that requires a little bit more time before we get there. So we're gonna, like I said, we're gonna set up our 4 buffers. We have our position, we have our velocity, we have our age, and our life. And we're going to use only 4 particles. So that's particle 1, 2, 3, 4. Our starting position is origin. And our starting velocity is 1 going up. So it's going straight up. And we're giving our age. Now, as you can see, I put it age at negative 9,000. Because I want the first frame to hit that loop where the age is greater than a life. I don't know why it's negative, but I guess for some reason it's negative or something. Because at this point, because I want it to fill in our velocity and our position, but it's going to reset the position back to 0. But I want it to reset. I want it to do a random velocity in the shader code. So I'm not have to deal with any random function calls in here. I actually let the shader actually initialize our velocity for us. So that's why that's why I'm doing it that way. So I'm passing in an age. That means the particle is already dead. Reset it for me. So that's why I'm giving it an age. So if I didn't want the shader to kind of do that work for me, I would just set age as 0. So yeah, I left a comment here to explain. It starts at 0, blah blah blah, and it needs to be negative so that the 2 cancel out and makes it a positive. Okay, so that's why it's negative, and I spelled positive wrong, because it's age minus age, so it needs to be a negative. So a negative minus a negative makes a positive. See, that's why comments are very important, because I looked at it, like, I don't know why it's a negative, but it has to be, and there. My comment now explains why. I'm trying to negate a negative in the shader code. And then of course I'm setting the life. So particle 0 has 8 seconds. This lives for 5 seconds, 3 seconds, 7 seconds. Why is it in thousands? Well, this is because the time that I'm pushing into it is in milliseconds. I'm thinking about maybe down the line when I start abstracting this, I'm maybe set it up where I automatically divide. So you put it in where time is going to change from milliseconds to maybe seconds, or like a fraction of a second. So this way you can then just easily just use seconds instead of milliseconds. I don't know if I should keep the time in milliseconds or should I do time in seconds themselves. I'm not sure. If you guys have a preference or a reason why one should pick over the other, please comment, because I'm actually curious. I'm really not sure how I want to go. Seconds to me seems like more of a pain in the ass because I have to make these bigger values. If I do seconds, I can do it's a lot simpler. It's just 1, 2, 3, 5, 7. I don't have to make myself or any other developer or programmer have to think in milliseconds, because I think Unity and everything else, they do things in seconds. So yeah, leave a comment if you have a curious, but for right now, all time exists in milliseconds, so that's why it's in the thousands place. So that's really just 5, 3, 7 seconds. So I'm setting up the life. And like I said, I'm not changing the life in the shader. So these are static. But you can then afterwards kind of make these random. Now we're going to have to start actually setting up our buffers. And we're going to build our buffers from scratch. We're not going to use our abstracted boilerplate code that we've made in previous videos. We're going to start everything from scratch. So we need to create an array. We need to create our two buffers that we're going to be reading and writing from as we alternate frames. So we're going to create an array of VAOs. These are, remember, if you don't remember, we're going to have a refresher course on how to create VAOs and buffers again. And if you're new to the series, even better. Now you're getting some new information. So the first thing we're going to do is we're going to create our VAOs. So we're going to create an array of VAOs. So this way, both VAOs, I'm trying to think, both VAOs have to be identical. So we're making an array. So this way we write the code once and we just loop it twice. So there's, and on top of that, we have to create our transform feedback. And like I said, the way they're put together is identical to VAOs. So there's our VAOs and there's our feedbacks. And we just save our values back to our emitter because we want to save them so we can reuse them. And then I need to save a total particles that we're using. And I just use a life because it's a simple array. Because if I go here, I have to take a length divided by 3. I don't feel like doing division. So since this is an integer value, I can just, or a simple value, I can just do that. Oops, don't drag it. And V. And what's V? I don't remember what V is. Oh, V is our buffers. So we have a, I don't know why I did it this way. Because I had to create 2 buffers. Oh, okay. All right, I get it. Okay, sorry. So V's are an array. This is, and we're saving that array into here, and then we're going to make each element a structure. All right, so that's how it works. I know I wrote these things and I always forget. It's been almost 2 weeks since I've done this. I did this 2 weeks ago. I've lately been doing 3D modeling for one of the lessons, and it's taken me a while to make it. So that's why I'm kind of forgetting about how particle systems work. So the first loop, we have we're going to create our buffers. So first thing, like I said, we're going to create all our buffers. We got our position, our velocity, age, and we don't need ID. Let's just leave it in there so I don't want to break anything. I took that out. Yeah, I took that out. So we don't actually need that. That's gone. Like I said, I was prototyping, and then I used ID for something, and then eventually I started using the GL vertex ID. So I didn't want to use the ID anymore because it's an extra buffer, and I can actually kind of get an ID value straight out of GL for shaders. So that's why that's there, but no longer there. It's when I start going through the code and start optimizing and taking out all the garbage. So we're going to create our 4 buffers that we need. These are our they're essentially both our attributes. Oh, wait, these are attributes. I think these are called attributes. Attribs, because they changed it to ins now. So they used to be called ATTRIB, I think, or there was spelled the full name, but whatever. Yeah, these are the attributes, and they're also going to be our varings that exit out. So these are the buffers that we're going to actually pass all this data into. You can probably skip a lot of it because this is a lot of old stuff from many videos ago. So the first step in building a VAO is we need to bind it. So we're going to bind it, and then we're going to have to build each buffer individually. So we bind our buffer because this actually just creates a buffer ID. We define our buffer. What type of thing it is, and normally we use static or dynamic. This one we're using stream copy. There's actually a bunch of new ones. There's dynamic copy. It's just these values that allows us to GL to know that okay, these buffers are going to be modified by the GL context or by the graphics card itself. It's not going to be user updated. It can be user updated, but it's going to be updated by the thing. So I try to remember. I just use stream copy, but look it up if you want, if you're more detailed. But there's like a dynamic copy, and there's a couple of other ones. But for today's instance, we only need stream copy, and it doesn't matter. You can switch to dynamic copy. It's just how GL kind of stores the data, so it can optimize the way it reads and writes from it. That's what all these static and dynamic things are all about. It's just optimizing storage. So we would define it as how the method of storing the data, or how we're going to be using it. Like how often we're going to update it, and then we set up what type of information it is, and I put up here. I saved it up here so I have a reference to what the shader uses. So like that's 0 position, that's 1 position. That's how big the component is. So there's 3 components in it, and we're not using stride, and offset. So we got our 4 buffers all set up. So quick and easy. And then we unbind our buffer because we don't need to use it anymore. Now during our VAO, we're going to bind our transform feedback. And then we're going to just bind the buffer to the VAO, or not the VAO, to the positions of our feedbacks. And I built these positions in the same order as this. So this way they both, that's 0, 1, 2, order 3. So we're telling a buffer saying, I think actually it doesn't really matter the order over there, but so basically saying this buffer ID at that index is going to be a buffer that can be modified by the GPU. So we're just defining which buffers can be defined by the GPU, but you have to use the exact same index values as our attributes. So that's why I kind of built make sure you build everything in the same order. So everything's kind of important, I believe. So yeah, so once you're done, you just unbind our vertex array, and you're done building the feedback transform and our VAO. And that's really how during this loop, you're passing in all the data, and you're passing it in twice. So all this data gets duplicated twice for both VAO buffers. So now that we set up the emitter, then you have the draw function. And oh yeah, I probably forgot to mention at the very end, we set the current VAO we're using, because remember our VAO is an array, so we're going to go bouncing back and forth between 0 and 1. So get rid of that constructor. This is probably not here anymore because I was using it as a shortcut and I got rid of the shortcut. Just leave it there for now. So that's garbage. You really don't need that because, like I said, I forgot to clean up a couple of small things. So we're overriding our draw function from our renderable, because when we're drawing with TransformFeedback, we need to do a couple of things. Like I think this is like the original, what the function originally looks like if we didn't override it. So we're going to get the next VO. So if we're at 0, we want to get 1. If we're at 1, we want to get 0. Essentially, it's basically saying which one is the one that we're going to write to. So our current VAO is where we're going to read from. The next, the other one that we have, we want to use it as our write. So one's a read buffer, one's a write buffer. So our current is our read buffer, and then by calculating this, so let's say if it's 0, I'm going to add 1. We can do a modulus 2 to make sure we stay between 0 and 1. So if it's 0, it's 1. So index would be the T feedback of T feedback of 2. You keep them as separate, don't we? I probably forgot to mention that. Yeah, that's right. They're 2 separate arrays. I forgot to mention. Yeah, they're 2 separate arrays. Like essentially, like these feedbacks actually point to these VAOs, but they're the way they're used is like conduits. It's like it's the gateway to get into that VAO buffer. That's what these really are. They're just conduits. They're portals. They're wormholes. Whatever. They're pointers really. And I mean, if you get down to C++, they're really just pointers to the buffers that we created in the VAO. So we're saying, if you take it in a C++ kind of context, is that we're getting our VAO pointer and we're getting our feedback pointer. So this way we know which feedback group that we're trying to use, because like this feedback group basically essentially create pointers to the buffers, because it uses our buffer ID that we generated. So it's basically pointing to it. So it's a pointer, in all honesty. But it kind of sucks to use C++ terminology or ideas in JavaScript, because even though it does exist, it's there. It functions very similarly, except the fact that you can't change the addresses mathematically. But a reference is a pointer. So in essence, I try not to confuse you guys. I know like dozens of programming languages, so I try to keep this strictly JavaScript. Right. So that's what we're doing. We're trying to find our read and we're trying to find our write. So, and since they're connected, so we don't want to use the feedback that connects to the current VAO. We don't want to use that one because we don't run a write to itself. I think when you're reading from a buffer, you can't write to the buffer. It's kind of locked. That's why you need a second buffer to write to. So since it's locked, we're going to the next VAO, and we're going to say we want to use that feedback portal, that feedback pointer, to the next VAO over. So that's like I said, that's why I'm kind of using the words like portal or pointer, because it kind of just gives you access to what's in the other VAO. So to start rendering, we need to bind our VAO, so it's our current VAO, and we also need to bind our transform feedback, and we're going to use the feedback of the other VAO that's not being used at the moment. So we bind, we pass in our time. That's why I said I wanted this to be global, so I can have a quick, easy access to the current time. So I pass in the time to our shader. And then we have to begin our feedback. Then we can draw, and then we end our feedback. And then since we have the next index that we were writing to, so index was our write index, we're going to say, well, next loop, the write will now become the read. And that's how we alternate back and forth. So we get a read, we get a read, we get our write, and then at the very end, we save our write index. So the next loop, it becomes our read index. It becomes our reading pointer. And that's how we start alternating between VAOs. Excuse me. And that's all everything you need to do begin to do our transform feedback. So when you draw, you have to do that. When you're creating buffers, you got to create pointers to those buffers. That's set up in a transform feedback kind of object. That, like I said, like transform feedback functions as VAOs. VAOs is a collection of buffers. Transform feedback is a collection of pointers to buffers. So it's a collection. They're kind of like structs. and I think in the GPU they're treated as like these pre-existing struct values. There's like, so it's like predetermined how many buffers you can have. I forget how many. There's like a limit. And that is all the code we need for transform feedback. So if we go, and it's array looping, as you can see, when I refresh, everything goes straight up in the air because everything got spit to the GPU at the same time. But once each one has its own lifespan, then you start seeing them work correctly. There is a ways to kind of start up a particle system where for every frame you just add on and you update the buffer on server. So this way you can instead of having everything kind of shoot out in the air, you can then build up the buffer, and once you're done building up the buffer, it then it'll kind of just take care of itself. I'm gonna see if I can find another way to do it, like set up like a delay. So this way everything's kind of hidden until a certain delay value sets up. So this way you don't have to. So this way you can kind of set up everything in one go, and not have to worry about actually feeding the data in. Just to get that initial startup. So this way you can have 1, 2, 3, 4, instead of having all 4 or all 1,000 be thrown on the screen at the same time as initially. But I want this to be a very bare bones example of transform feedback, and very bare bones of particles. And here you go. You have particles that are randomly going in different directions. So if I go straight up, you'll see that they point in different directions in that circle that we're trying to determine. So it starts at origin and just shoots at random directions, going straight up that funnel, and the life is dependent on each one. Some die sooner than others. Now, if we want to have some fun with the shader, we can do a couple of fun things. Like right here, we can change its. Let's say we want to change its size based on how old it is. To make it more visually easy to tell, I'll change this to 20. So the older it gets, the smaller it gets. So that I'm taking life, and this would end up giving me a value between like 1 and 0, where like the age is 0 and that's 1, but I want to invert it. Because I don't want it to get small to big. I want it to get big to small. So that's why I'm doing -1. So I'm trying to reverse the age value. So this way I can go from big to small. So the older it gets, the smaller it gets. Instead of the other way around. And sometimes this doesn't refresh very well. There you go. There you go. And now visually they look like. Let me zoom back out. Looks like they're going away from you, but it's just the visual effect of it getting smaller. So, but like I said, you can now start messing around with it. You can actually start doing funny things with the points. So now we gave it a size. So we're changing its size based on its life. Another thing we can do, which I commented out earlier, is that we can add gravity. We can start adding gravity. So for every frame, we're going to take velocity. We're going to update its velocity by removing some gravity value. So our gravity value is 0.1. So our x and z position stays the same, but its y position changes. We're trying to make, because our velocity is pointing straight up, so we're going up to a very high velocity. So we're going to do any value between a random number between 0 and 4, but initially it has to be 2. So it's a value between 2 and 6. So that's going to be our initial velocity going straight up. So maximum speed is going to be 6 units per second or something like that. And for every frame that after that, we're going to start chomping away at the velocity on the y position. So once we start adding gravity to our velocity, there you go. Now everything starts to drop down. Now they're not going straight up in the air anymore. They're kind of just coming down. And this is what allows you to create that fountain effect. So you can have water sprouting up and coming back down. So if it had like tons of vertices, it will look more like a water fountain. So now you've seen how to shoot something straight in the air. You see how to apply some size effects to it. We're changing its size based on its age, and we're changing its direction. Instead of going straight up, we're going to change its velocity per frame. And like I say, if you want, you can add random age, so that its age or its life can be different. And the last thing I wanted to show you is that since we're doing points, and we haven't done this before, there's something in WebGL called GL Point Coit. And GL Point Coit is available when you're drawing points. So we have our draw mode as points. We have access to this value. And what this value is the UV values of our point. And our point is really just the quad. So when it's rendering that quad, it does have a UV value. So since we're drawing it and we have access to it, we're using, if I use that, and we've done this in previous video, so I don't know if what this does, it actually changes it can actually draw a circle in the quad. So that's what we're doing here. So with that saved, so instead of seeing squares, we have circles. I don't think I have blending turned on, do I? Yeah, I have blending turned on. Now we have squares. And like I said, if I had thousands of these, which I'm not doing today, it'll probably start looking like a water fountain, because you have like sprouts of water going, flowing in random directions. And they have gravity because they're coming down. And normally with a fountain, to make it perfect, you kind of maybe its up velocity should be equal, so this way it's always very evenly flowy, since I'm giving it a very random upward velocity, speed and everything else, so everything kind of is different. But yeah, that is it for today. Feels like we probably did a lot. Like I said, if you can actually use this with textures too, so you can apply textures to your points. So if you pass in a texture, you can use these things to render out a snowflake or anything really. So you can use points as quads themselves. The only problem with points is that they're a billboard. That means they're always pointing the camera, which could be a good thing in certain instances. Sometimes, like I say, if you're doing snowflakes and you just want to see the snowflakes falling, you want always to point it, because you don't want it to be at an angle and the snowflake looks a little funky. Or if it's perfectly perpendicular to the camera, you can't see it at all. At some point, maybe I'll do like something like that. I'll get like a snowflake texture and then set up a particle effect that starts up here and then snows. So this way you have like a snow effect happening. That might be a fun effect to do in the future once our particle effect system is built up a little bit more. Oh, that's right. It's the wrong blending mode. That's what I'm saying. All right. You have to use a different blending mode when you want things internally to mesh together. But like I said, this is bare bones. So right now, the only problem with our particle system that we have is that we need to pass in everything like this. So let's say if I want to do a quad, I have to pass in 6 points and then rinse and repeat. So if I want like 100 quads, I have to do 6,000 things. So in the next video, we're going to integrate instancing into our emitter. So this way we can actually set up a single point and then maybe set up a bunch of attributes for that point. So it'll be our instance values. So this is a way we'll have a single point, and then that mesh, because you can consider this a mesh. This mesh will be then duplicated based on the other attributes. And hopefully those attributes is what the feedback gets updated. Like we might need another buffer where we're going to have a position which I haven't really worked it out, but like this stuff will be static, and then we're gonna have to have another buffer of like starting position. And a position is really just our vertices. So this would basically be a pose will then be part of our maybe instancing buffers. So why do we need instancing? Well, the idea is that like say if we want quads. So if we want quads, we only have to set up the quad once, and then we tell the GPU, here's our quad, repeat it like 1,000,000 times, and here's all the attributes for those 1,000,000 quads. So it'll draw the quad, and that one quad will have that one velocity. It will have that one age. It will have that one lifespan. So that'll be in the next video. So we'll add instancing into it. So this way, once we have that in there, we can do quads. We can do really funky shapes. Like I said, the Dragon Ball Z power-up aura needs a funky spiral mesh that gets textured. And so, like I said, it's something I saw someone do, and I want to do it. So we need instancing, because we can't add a funky mesh repeatedly. It would be very difficult to do it. So we definitely need instancing. We need transform feedback. That makes those type of effects easy to create on WebGL. So I don't know when that video is going to come out, because I'm trying to do some armature stuff. So depending on time, maybe I'll make a quick video, another video for particle system, because I'm really busy. Like I said, I'm just having a hard time getting the 3D modeling done, because I'm actually modeling something, and that's going to be our character that we're going to use for a lot of our armature stuff, because I want to do animations and things like that. And one of the things I want him to do is power up like a Super Saiyan. So I need particle effects, and I need the mesh, and I need things set up to create silly little things like that. So I'm thinking about making this a separate side series, kind of like a sub-series to the WebGL, where once we have the particle system mostly put together, like all the bare bones that we need to get it working, and abstract it away, and from there, that little mini series will then go into actually building effects, like bringing textures and meshes from other online tutorials, that how they do it in Unity, or maybe it's something I can kind of come up with my own by looking at other people's effects and saying, okay, if I do this, if I do that, this is how we can go about building something similar. So yeah, that's it. So we're gonna start having some fun once the emitter is done. So once we have the emitter set up, it's like that's really neat. It's the instancing. Once the instancing is done, then we can start doing some simple effects. Yeah, so we're gonna start doing some simple things. We're gonna because Unity effects have like tons and tons of features, like the ability to change the scale, change the position, change the opacity. There's like boatloads of things, and it's like there's a little UI. You kind of just change all these values, and for us, we don't have all that. We can actually build every little bit of it. So I want to see if we can build all the little pieces, and then maybe at the very end, once we have all these fundamental pieces that we can interpolate between, like I said, interpolate between size, scale, between position, between colors. How to transition between a set of gradients. I've been looking up how to do gradients in GLSL. Did I use that right? GL. What the hell is it? GLSL? I forget the name of the shader language. But yeah, there's like a lot of things. We got gradients, position, maybe changing textures between the lifespan, and maybe animating textures. To create fire effects, you sometimes need to have quads that the textures actually change in between. So you have like a wide explosion to like a small explosion, the funnel smoky thing. So creating fire effects, you need to animate textures while you're moving things around. So like I said, there's a lot of fundamental pieces of a particle system. So once we have all the fundamental pieces together, then we could come up with a way to build a tool or an effects builder. So this way we can then mix and match the pieces, and it will actually create the shader for us that utilizes those pieces. So right now we have to write all the shaders for us for every individual thing. So that'll be something, hopefully, the end goal when it comes to particle systems. It's you have a whole collection of things you can do to a particle, and then you can mix and match, and the shader gets created for you based on those features. Just basically how Unity does it. Unity gives you all these features, and it builds the shader for you in real time to perform those effects for you. So I hope you like the idea. This is going to be fun. So yeah, this is probably a very long video.